I am Manchen Wang, and this is my lab report for Physics Lab 1. Here are the several parts that I'm going to introduce in the lab report: the introduction, experiment, model and coding, discussion, and conclusion. The first part is introduction. The purpose of this lab is to examine the possible results in real life if the object is moving at a constant velocity and a determined speed. And I will also compare real-life result with computational model to see the difference. And my assumption made is that the position versus time graph of the computational model and the graph of the experiment model would overlap. And the result is that there was insignificant difference between the two graphs. So the fundamental principle behind this experiment is the Newton's first law. So the Newton's first law says that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of the external force, which means that when the net force on an object is zero, the object would move in uniform motion as described in graphs here. So this is our experiment, and this is the experiment video we recorded. We used equipment from the physics lab to minimize the friction between the object and the track of the object. When making the computational model, to make the model represent more of the experiment model, I made the positive axis pointing to the right, like I did in the tracker, and made the object to move from right to left. And in my coding, considering the time difference between data points we collected in tracker to be 0.16 seconds, I changed the original I changed delta t into 0.16 seconds and changed the original negative 0.37 meters per second of the object into negative 0.0603 per 0.16 second. And I also changed the length of the computational model to be 3.68 seconds, and just like my video recorded, and I also made fnet equals to 0 on all direction because we are modeling a uniform motion. And here are data we collected from tracker for the observed model and from GlowScript for the computational model. Here is the graph when you plot all the data points into a graph. And you can see that there wasn't significant difference between the two lines. Here is my discussion. And the first part is about the follow-up questions. So what if I made a different choice of orientation of the axis? So if I flip the axis from right to left or flip my video, I would gain a graph that would be more similar to the y equals x graph. And if I started to analyze the video from the moment the object is being pushed, the speed would experience an increase at the first few plot points. And what does the mean question asks about is it possible for me to say how many pushes and pulls that are required to make net force equals to 0? And I don't think I am able to answer the question if I can't measure the friction force between the object and the track. So the second part of discussion is about the comparison of the two graphs. The difference between the graphs were minimal, especially in the beginning when the effect of friction was insignificant. Yet when velocity started to decrease in a significant amount to the naked eye, there is a difference in the position to time graph. Not velocity, but the speed. And the friction force between the object and its track and air force can be the source of difference between the experiment data and the computational model data. As shown in this graph here, when the object is moving on horizontal direction, there was only force of the friction, but there wasn't any force to counteract toward these friction force, which will eventually make the object to stop. And here is the conclusion toward my assumption. For most parts, the dataset from the experiment coincided with the data from the computational model.